So we now continue our internal force analysis and consider the case of a distributed load with the distribution function W. Now, as per our previous analysis, this weighting function has units of force over distance, so it's pounds per foot or newtons per meter. So first of all, let's consider the simplest case where the weighting function is a constant. So this is say uniform over the length of the object, and one example of that would just be the weight, because of course gravity pulls down on every little mass element along this uniform beam. So it's 4 meters long, and the weight distribution function is 3 newtons per meter. And as per our previous problems, the first thing to do is external force analysis. So we see a roller joint at A. We see our coordinate system there. We'll just use the standard one, y, x, z out of the page. So we'll have an upwards force at A. There's a pin joint at B, so there is a y component of the pin force and potentially an x component. Now, the other force we'll have is the resultant of this distributed load. And the first thing we're going to have to do now is figure out how much that is. Oh, bother. All right. Yes, we also want to figure out where it acts, and that's the centroid. So, the way we, of course, figured that out is so the total weight will just be, I guess I called it F earlier, here I'm calling it W. It's going to be, that's capital W. It's going to be the integral of little w dx. Now that is a constant, it's just 3, and then x is running from 0 to 4, because it's 4 meters long, and so that's just 3x from 0 to 4, that's just 12 units. I guess it's 12 newtons. Now for the centroid, that's the integral of wx dx over the integral of w dx. And so both of these are from 0 to 4, 0 to 4. So this is the integral of 3x, and the denominator we've already done, it's just 12. Now, because, of course, this is a uniform distribution function, we expect the centroid to be just at the middle. So the integral of 3x is 3 x squared over 2 from 0 to 4 divided by 12. So that's 3 times 16, that's 48, divided by 2 is 24, divided by 12 is 2, and this is in units of meters. So yes, indeed, we've got 12 newtons, which is the net resultant of that distribution function integrated over the entire length, and we have the centroid at 2 meters. So now we're in a position to do our external force analysis. So we're going to sum y forces, and so we've got the roller support at A, we've got the downwards capital W, and maybe I should make it look like a capital W somehow, and then we've got the pin force By. Those have to sum to 0. Summing x forces, we see that the pin force Bx must also be 0, since it's the only horizontal force here. And then let's take our moments about A. So we've got an into the page negative moment of the weight acting at the centroid, which is 2 meters. And then we've got a positive out of the page moment coming from By, that's acting 4 meters away from the point A. And so with the weight of 12, we see that By is 6, Bx is 0, and A is 6. So there's the result of our external force analysis. Now, the next thing to do is to make a section and do internal force analysis. Now, in this case, I suppose if we read the fine text of the problem, we were looking for the internal forces at a point 2 meters from A, so the midpoint of the beam. Changing the slide. So we make a section 2 meters, and that obviously leaves 4 minus 2, i.e. 2 meters on the other side. And so we're going from A to X. Now we already know the support force at A is 6 newtons, and it's a little larger, there we go. And we are going to have for our forces on this section, we will have its weight, which will act at the centroid of this section. Now, because this is 2 meters long and a uniform distribution function, you can just integrate, well, all right, I'll write it out. So we're just integrating 3, which is the little w, the distribution function, from 0 to 2. That's just 3x, that's just 6 newtons of weight. And then, again, it's uniform, so the centroid will just be at the middle, and that's just at 1 meter. So there is the weight of the section, capital W, maybe I'll call it W1 to distinguish from the previous capital W, and then we add on the internal forces to our diagram. So this is the tension, N, the shear force, V, and the bending moment, M, in the usual sense. Okay, now we apply the conditions for equilibrium to do the internal force analysis. So forces sum to 0, and we usually take moments about the point where we made the section, so that'll be moments right here about the cut end. Therefore, we need to know the distance from the centroid to that pivot point. Again, it's pretty easy since the centroid is 1. This weight function W1 simply acts 1 meter from this point here. Let's call this point here X. So X is a location where we've made the section. It's kind of crowded there, so I don't quite know where to put it. Somewhere in there, I guess. Maybe where I had it's the best location. And now let us do our internal force analysis, which really just involves applying the equilibrium conditions to this section, to this AX section of the beam. So we sum X forces to 0, and there's just the tension, so that's 0 in this section of the beam. Then we sum Y forces, and we've got upwards at A, which we know is 6 newtons, downwards the weight of the section, which we calculated to also be 6 newtons, and then downwards the shear force summing to 0. So we can see there's 0 shear on this section. At this point, 2 meters from the point A, there's 0 shear, I should say. And then we sum moments about X, and then we've got the AY force. Now taking, doing R cross F, we see that's an into the page negative moment. So the AY force acts 2 meters from the point X. Then we've got our weight moment, and then that would be an out of the page positive moment. And that acts 1 meter away from the section point X. And then, of course, we have the bending moment M. And all of those must sum to 0. So that gives us N is 0, the shear force V is 0, and the bending moment is 6 Newton meters, because we get negative 12 plus 6 is negative 6 on this side. Throw it over to the other side, and it's positive 6. So that's our first internal force analysis with the distributed load, a nice constant load distribution function. Now we did that at the point, at a point 2 meters away from the roller joint. The next thing to do is to do that same calculation, but now at a variable distance x away from the roller joint. Our analysis will be very similar to the first example, and the good news is we've already done the external force analysis, and that certainly doesn't change at all. So let's change the slide here. So, hold on, let me just go a bit more slowly here because I've got all these things in the way here. So we're making this section now. Let's move this stuff out and we'll build it together slowly. Hopefully so. No, all of these things they're not stuck together like I usually make them. Okay, so the first thing to note is that we're making this section at a distance x from the point A. So it's not 2 meters anymore, it's x. Come on, you. All right, it's not cooperating. And so we draw our forces. So obviously we have the force A, which is upward 6 newtons. We don't need to do external force analysis since we've already done it. So we know that A is 6 newtons. And then we're going to have the weight of this section. Now we are going to have to integrate here because we're going out to a distance x. And that weight, of course, acts at the centroid. So we are going to need to know as well what the centroid of this section is in order to do the moment calculation properly. So let's start perhaps just by doing that calculation. So our section weight, it's still a constant function, but now we're integrating from 0 out to x by distribution function 3 dx. So that's 3x from 0 to x. So putting in 0 we get nothing, so it's just 3x. Next we need to know where the centroid is, measured from the point A. Now, if you were to work this out formally, say if the load distribution function were not constant, then you would have to do it formally. It would be the integral of the little load function times x dx over the integral of the load distribution function. So this is just the integral of 3x from 0 to x divided by a previously calculated section weight. And so 3x gives us 3x squared over 2. We divide by 3x, and we get x over 2. So no surprise at all for this uniform distribution function, the centroid is just at the middle of the structural element. Now, when we go to do our internal force analysis, we're going to want to know how far that weight function acts from the section. So that's just x minus the centroid, but again, that's just x over 2. So let's make a section at the point x. And again, it looked like putting the label x there was a good spot. And then we consider, or we add the internal forces to the force diagram. They are, first of all, the tension N. Let's make that label a little larger. Then we have the shear force, V. Again, let's make that label a little larger. And these act in the conventional direction. So because the XB section tends to push down on the AX section, the shear force is taken to be downwards. And finally, we have the bending moment M. So all of these taken to act at the section point X. Now the XB, sort of the rest of the beam, that will have length 4 minus X. And you could do your internal force analysis on the XB section and get exactly the same answers. All right. So as I say here, the distance from the centroid to the section point is x minus the centroid, which is again just going to be x over 2. But if you had a more complicated load distribution function, you'd have to go through that calculation algebraically. So we have determined the weight of the section, and we have drawn the internal forces. So now let us do our internal force analysis, which simply involves writing out equilibrium conditions for the section AX. And when it comes to do the moment, we take moment about the section point X. So here are the equations. So summing X forces, well, there's only the tension, so that's 0. Summing Y forces, we've got upwards 6 newtons at the roller joint A, we've got downwards the weight of the section, I call it W3. Maybe I'll just write it in as 3x here. And then minus the shear sums to 0. So because a is 6, you can see that v is going to end up being a function of x. Well, let's just summarize right here and now. So v is going to be a minus 3x, 6 minus 3x, or minus 3x plus 6. So the shear force is a function of the distance x from the point A. Next, we sum moments about the section point x. So now our negative moment from the roller joint, and just take a second to do the right-hand rule in your head there and see that it is a negative into the page moment for the force A. That force A acts a distance x away from the section point, and x is a variable. Then we have our W3, which is a positive out of the page moment. The weight is 3x, and the distance from the section point is x over 2. That's the distance that we calculated right out here, from the centroid to the section point. And then, of course, we have our bending moment m. Those must sum to 0. So if we solve for the bending moment m, we see that it's a quadratic function. So it's going to be negative 3x squared over 2 when we bring it to the other side, plus ax. But of course, a is 6. It's minus 3 halves x squared. It's plus 6x. Now, having done this, it would be conventional to do a diagram. So just let me pause the video and then produce the diagram, and then I'll show it to you. Okay, so there's a quick sketch of the graphs. So a few things to notice. Where the shear force reaches 0, because the shear force is the rate of change of the bending moment, dm dx, that's where the bending moment reaches its maximum. So it's a quadratic function, so that's where the vertex of the quadratic is. And then also where the v function is the maximum, so its maxima are plus 6 and minus 6, that's where the quadratic is the steepest. So you have the largest rate of change of bending moment at the two extremities. So that is what the graphs of those internal forces look like. And so that analysis was for a constant weight distribution function. In class, we'll look at a variable weight distribution function and repeat the internal force analysis.